Hello, and welcome to a bonus episode of Sam's MCAT Basics. In this podcast, I'm briefly going to discuss what the most important organic chemistry reactions to know and have memorized are. Which mechanisms should you know? Which ones don't really matter? I came up with this list a few different ways. The first was reviewing all the practice material by the AAMC. You could pick out a few that came up a few times. And then also I went through, some blog posts, some stuff from studentdoctor.net, Reddit, kind of see what the consensus was in terms of which reactions are most important to know and have memorized for the MCAT. And so then this podcast is to essentially say, okay, these are the ones you need to know. I'm really not going to go in too great of detail, and that's just because, when you're memorizing these mechanisms, it doesn't help that much to have somebody say it to you. It helps really to have it drawn out and see it for you. And this is a podcast, I can't really do that. So that is why this is a bonus episode. It's going to be real quick, but hopefully you get what you need out of it. And it helps you understand which areas you really need to focus on in terms of studying for organic chemistry on the MCAT. So here's what I've deemed as the most important reactions to know. So you have SN1 and SN2, which are nucleophilic substitution reactions. Then we have carbonyl substitution addition reactions. We have aldol condensation, oxidation and reduction of alcohols, which in this case you don't need to know a mechanism, just need to know the reactants and the products. And then Fischer Esterification and Saponification, which is the kind of the inverse of Fischer Esterification. And then lastly, you need to kind of know a little bit about E1 and E2 reactions, which are elimination reactions. I'm going to throw in a little bit at the end about which IR and MR values to know. They might give you some kind of spectra and say, okay, we have this peak here, this peak here. What functional group does this compound contain? And if you don't have these values memorized, you're not really going to be able to answer those questions correctly. All right, so now that I've introduced these different reactions, I'm going to cover some of the concept behind them, All right, so now that I've introduced these reactions, I'm going to cover a little bit of the background on them, a little bit of conceptual stuff to know about them. But in the end, really know the mechanisms, know how to draw them out, understand them. What I'm going to talk about is more concept-based. All right, so first let's talk about substitution reactions. This, again, is SN1 and SN2. So these are probably the highest yield OChem reactions that you're going to see. And essentially what happens is you have a substituent group that leaves and is then replaced by another substituent group. And you have what are called a nucleophile and electrophile. Again, the nucleophile is a compound that donates an electron pair to form a bond, and an electrophile is a compound or an atom usually that accepts an electron pair to form the bond. So in SN1, it is a unimolecular nucleophilic substitution. And for SN1, it's a two-step reaction. So the first step is the rate-limiting step. And in this first step, you form a carbocation. This is where the leaving group leaves, and you have this positive charge on a carbon, which is a carbocation. And this is the rate-limiting step for this reaction. This carbocation usually doesn't form very fast, so that limits the reaction rate. In the second step of the reaction, the nucleophile comes and attacks that positive carbocation and forms a bond, and the substitution is complete. Now you have this new bond formed to this new substituent group. So again, that's for SN1. Now we also have SN2, which is a bimolecular nucleophilic substitution. And in this case, there's two really kind of important things to know about this reaction. Number one is that it is a single-step mechanism, so it's called a concerted mechanism. Your nucleophile comes in from the back, and it attacks that electrophile, which is typically a carbon, and then your leaving group leaves, and that all happens in one step. And so because of that, you have an inversion of stereochemistry. All right, let's talk real briefly now about carbonyl substitution and addition reactions. So carbonyl substitution reactions are reactions between some kind of alcohol and a carbonyl. And a carbonyl is simply a carbon double bound to oxygen. And in this case, when you have substitution reactions, this carbonyl either has to be a carboxylic acid, an ester, an anhydride, or an amide. And so essentially, you have to have some group that can leave. You have to have some kind of leaving group. And so what happens is you have this carbonyl and this carbon that's delta positive. The electrons are being pulled away from the carbon by the oxygen, which is much more electronegative. And it has that delta positive, and you have some alcohol that comes, and the lone pair on that alcohol, on the oxygen specifically, comes and attacks that carbon. That bond breaks. Your group that was on there before, let's say you had a carboxylic acid, it's an OH that then leaves, and then you reform that carbonyl bond or that carbonyl group. Addition reactions are very similar in a lot of ways. The key difference here is that addition reactions happen when you have either ketones or aldehydes, right? Because ketones and aldehydes don't have these leaving groups that can leave. So what happens is you have the same thing happen where you have some kind of nucleophile. It comes in and it attacks that carbonyl carbon that's delta positive, and you have a bond that forms. But this time you have no leaving group. So that nucleophile just adds on, and you end up going from a carbonyl to now a OH or a alcohol group, if that makes sense, a hydroxide. So again, the keys are this. For substitution reactions, you need to have some kind of leaving group, and that either comes from a carboxylic acid, ester, anhydride, or an amide. If you don't have those, then you got to think, okay, I have some kind of addition reaction here, and that happens in the case of ketones and aldehydes. So the next reaction to know is called Aldol Condensation. And in this reaction, you have a carbonyl nucleophile that attacks another carbonyl. So I like to think about it a little bit like this. Have you ever taken your sibling's hand or your friend's hand even, you take it and you grab their wrist and you start making them hit themselves. And you say, why are you hitting yourself? Why are you hitting yourself? So this reaction is kind of like that, right? It's a self-attack. So you're taking one molecule and another one that's the same, and they're both attacking each other. So it's kind of like making somebody hit themselves, right? Self-attack. Anyway, so in this reaction, what happens is you have a few different steps. So first, you have an alpha hydrogen that gets removed, and you do this part under very basic conditions. You need very basic conditions in order to remove that alpha hydrogen. So you remove that alpha hydrogen, and then you get a tautomerization that forms, a tautomer that forms, and this double bond that is in the tautomer then goes and attacks the carbonyl carbon. And this is step number 2 of the aldol condensation reaction. So the tautomer acts as a nucleophile. And again, this is coming from the same molecule. And yes, you can have 2 different molecules do this, but usually you'll have you'll just have a big tube of this one molecule, and then this will just kind of propagate naturally. So after this nucleophilic attack by the tautomer, you have the third step of the reaction, which is condensation. And condensation is simply the removal of a water group, or in this case, a hydroxyl group. And so again, this happens under basic conditions, and you have the removal of the alpha hydrogen, and then you have this water group that leaves, and you form a double bond in place of where that hydroxyl group was. So now on to oxidation and reduction of oxygen-containing compounds. So oxidation is simply an increase in bonds to oxygen or some halogen, or it's loss of carbon-hydrogen bonds. And reduction is just the opposite. It's an increase in the number of bonds to hydrogen or to some R group, and the loss of bonds to oxygen or some halogen group. And the most important thing to know here are the common oxidizing reagents and the common reducing agents. And again, remember, the MCAT is multiple choice, so really all you have to do is be able to recognize the names. Don't memorize them and be able to draw everything out. You don't need to know that. You just need to be able to recognize. MCAT is about recognition. So what are the common oxidizing agents that you're going to see? Common oxidizing agents are metals bound to large numbers of oxygens. Example of common oxidizing agents include things like KMnO4, H2CrO4. You can see these metals bound to large numbers of oxygens. And there's a few particular oxidizing agents to know. The first is PCC, or pyridium chlorochromate. And this is a weak oxidizing agent, and so it converts a hydroxyl group into a ketone or an aldehyde. And then we have a strong oxidizing agent to know, and it's called the Jones reagents, and this is a strong acid plus chromium O3 or CrO3. And this converts alcohol groups to carboxylic acids, so hydroxyl group to carboxylic acid. On the other hand, common reducing agents typically have large numbers of hydrides bound to metals, so things like lithium aluminum hydride, sodium borohydride, which are LiAlH4 and NaBH4 respectively. And the lithium-containing compound is a strong reducer, so it will reduce carboxylic acids. However, you can have weak reducing agents, and this includes NaBH4, and this can only reduce aldehydes and ketones. This can't reduce carboxylic acids. Okay, so let's get into the last two mechanisms or reactions to know. The first is Fischer Esterification and Saponification. They're kind of the reverse of each other. So esterification is where you create an ester. So to do this, you react a carboxylic acid in the presence of some alcohol, and it's a substitution mechanism. So it's the same as the reaction mechanism I talked about in terms of the carbonyl substitution. But this time you essentially are substituting a OR group for an OH group. And this creates an ester, which is why it's called esterification. And the reverse of that, which is where you start with an ester and you expose this ester to an alcohol and then convert back to a carboxylic acid, this is called saponification. And it's called saponification because soap was used, it used to be created by ester hydrolysis of fats. So this reaction used to be used to make soap. Kind of interesting. All right, the very last reaction to know is the elimination reaction. So again, just like substitution reactions or nucleophilic substitution, we have an E1 and an E2. So E1 is unimolecular elimination, and again we have a carbocation intermediate, a two-step mechanism. And then we have E2, which is a bimolecular elimination, and it's a concerted mechanism. So those compare to SN1 and 2. However, what's different is in these you have a deprotonation of alpha hydrogen, and you form a double bond, and then that eliminates one of the substituent groups. The key here is that you need some kind of strong base to deprotonate that alpha hydrogen. So if you're going through a question on the MCAT and you see, some reaction where there's a super strong base, and you have to somehow come up with a mechanism for this reaction, or they ask you to track atoms or whatever the case, think elimination. Now, quickly before I go, the last thing I said I was going to mention is what numbers to know for IR and NMR. And, put these on note cards, do what you have to do, but memorize them. So let's start with IR spectra. So the first number to know is 3,300 centimeters to the minus 1. And this corresponds to a hydroxyl group. And remember, this peak is going to be very broad. And then the next number to know is 3,000 centimeters. And so the units here is centimeters to the minus 1. Just a note. So 3,000 centimeters to the minus 1. And that's carboxylic acid. And then the next peak is going to be at 3,330 centimeters to the minus 1. And this is going to be a very sharp peak, and this corresponds to an amine group. And lastly, know that a sharp peak at about 1,750 centimeters to the minus 1 is going to correspond to a carbonyl group. Now moving over to NMR, what should you know there? So for NMR, know that an aldehyde hydrogen has a shift of about 9 to 10 ppm. And then for carboxylic acids, you're going to have carboxylic acid hydrogens, you're going to have a shift from about 10.5 to 12 parts per million. Then the last thing is an aromatic hydrogen will result in a shift on the NMR of about 6.0 to about 8.5 ppm. Hope this podcast helps you direct your studying, focus on these mechanisms, focus on these kind of concepts in OChem. Definitely, this is the highest yield stuff, and this is not to say you won't see some other stuff on there, but these are really the kind of the main things that people are in consensus about of where to target your OChem studying.